Welcome to today's lecture in cooperative communication systems, which is going to be about wireless mesh networks. Part 1 is the basics of them. I am David, I am a PhD at the Communication Networks chair, and as part of the wireless mesh group and the startup Meshmerize, we are developing a wireless mesh protocol for demanding use cases of mesh networks. So the content of today's lecture is going to be a rough overview of what a wireless mesh network is, especially in contrast to our today's everyday wireless networks. Then I'm going to present the basic building blocks of the mesh network, and thirdly put it into context of this lecture series. So at first, what is a wireless mesh network? It is not what we have in our everyday life as wireless networks, examples being cellular networks, which we connect to when we are on the go, and Wi-Fi, which we mostly use in our homes and workplaces. So these networks are hierarchical. They use a central entity, being the base station or a access point or router, as a manager and gateway for any communication in the network. Also being a single point of failure, because when you leave the coverage area of the space station or router, you also lose the functionality of the network. With these central entities being very powerful, also the demands on the end nodes are rather low. So if we call the central entity I in this example, these current networks implement something we call star topology, because any wireless communication has to pass them. So they are the sender or receiver of any packet. Whereas a wireless mesh network is fundamentally different from this. A wireless mesh protocol can use all available wireless connections, all available wireless links between the nodes in the network, thus implementing a network of equals, where any device can send to any other device, and also the tasks of the powerful central entity are now spread over the network, making the implementation more difficult. The result is a decentralized and non-hierarchical network, which has some advantages over centralized approaches. So for example, if any node fails or just leaves the network, the other nodes can make up for that, having a self-healing property of the network. So they find new routes around the loss of this node. If, on the contrary, a new node is added to the network, the nodes are able to discover this node, and the network is also auto-configuring, finding new ways to use this node, and so there's no engineer needed to set the connections and set the routes in the network. This makes wireless mesh networks scalable, and they also can be multi-hop networks. So they can be coverage extending as opposed to centralized networks, where the coverage of the network is limited to the radio range of the central node. Also, wireless mesh networks can be very cost effective. If you take nowadays 4 or 5G base station as an example, which easily costs more than 100,000 euros, a mesh node, mesh router is available for 5 to 20 bucks. this makes mesh networks good for a wide range of applications. So for example, the military, this is where mesh networks originate from the 1980s already, but also community networks like Freifunk in Germany or Gifi in Catalonia in Spain, where the internet access is spread over a large area, providing internet access even to remote places. Another example for static mesh networks can be in mining or in wind parks, extending coverage to underground or remote areas, where it also can be rather difficult or rather cost-intensive to put cables onto any windmill in an offshore wind park, for example. But they can also be used for public safety. Take fire brigade here. When they enter a building, they can be meshed with wearable devices, or also leaving maybe battery-powered nodes on the floor, informing each other about hazards or persons to rescue. More future-leaning applications can be in robots or drones, for agriculture and logistics, where cellular coverage cannot be guaranteed, especially for agriculture, but also in logistics, where warehouses are essentially metal boxes, which can cover up the radio waves. But also automotive applications are very interesting, where cars can warn each other directly using device-to-device communication about hazards like ice on the streets or accidents. So examples of current implementations of wireless mesh networks are just sometimes home routers that are now being advertised very often, which is sometimes just repeaters, but real implementations of mesh networks are, for example, optimized link state routing, which you can also look up in RFC. Then we have a better approach to mobile ad hoc networking, which is a widespread protocol which runs on over 1 million access points around the globe, and is also in the Linux kernel since version 2.6. The same is true for the protocol specified by IEEE 802.11s, which you can also find in the Linux kernel as Open 802.11s. OpenThread and Bluetooth Mesh are more targeted for wireless sensor networks, which are wireless mesh networks with additional energy constraints, where the sensors are often battery powered and have only very low computation powers to save energy. This is especially interesting for smart home applications, but also for logistics and production. So the second question is, how do wireless mesh networks actually work? What are the basic building blocks of them? So let's go back to our simple example. Let's assume S, we can call this node Susie, for example, or source, wants to send a message to D, Daisy, or destination. I will give you now a very superficial overview of the tasks and the structure of the mesh protocol. So in the beginning, no one is aware of other nodes. Those nodes are isolated, even though they have radio connections. So the first step necessary is to get aware of those connections. This is something we call neighborhood discovery, and when we discover our neighbors, we also adapt the links. So we'll have multiple bit rates, for example, and a modulation and coding scheme is chosen to get the highest throughput or most reliable link. So now let's assume we take this node K as an example. We could call it Carl, and Carl is now aware of its neighbors, being S and I and D, so Susie and Daisy and some node I, but this does not help Susie to reach her friend Daisy, because they're only aware of their neighbors. So the next step would be routing information calculation and dissemination in the network. So reaching multi-hop connectivity. The concrete step is that our node K, so Carl, is informing its neighboring nodes of its links or its neighbors. The difference of this is actually important, but I'll talk about this at a later point. So as an example, we can see that Carl now informs all its neighbors about its connection to D, but also will inform its neighbors about all its other neighbors. So that now the nodes can choose forwarders to reach other nodes over multiple hops. In this example, node S would know of node D, and that it can be reached via node K and transmit messages to D. But there also needs to be a backward direction in case a message gets lost over the notoriously lossy wireless links, which is covered with feedback and recoding. I'll come to the recoding point at a later time also. If we analyze these tasks now and put them into context of the OSI layer model, so we have the OSI layers at the right here, and we can see that task 1 pretty much fits into the abstraction of the link layer, as neighborhood discovery and link adaptation never leaves the domain of direct neighborhood. Whereas tasks number 2 and 3, routing information calculation and the spreading of those in the network, and the forwarder selection, so the actual routing execution, is very much a network layer, so a routing task. The situation is a little bit more complex for the 4th task, for feedback and recoding. So feedback can be link local only, so only from direct neighbor to direct neighbor, but could also be end-to-end, so over multiple hops, where it would be transport layer feedback, like TCP, for example, does in the internet. Also, the recoding plays a part here, but I'll talk about this later, as I said. So a mesh protocol might now use information from different layers to optimize its performance. And we could call this a cross-layer joint optimization, which is taking place. Here it's important to note that a mesh protocol does not have to use the transport layer, or does not have to perform tasks with the transport layer. You can just use TCP for this. And some mesh protocols also use part of the link layer of an existing physical implementation like Wi-Fi. This is optional, so to say. What we can note here, however, which is very important, is that the physical layer itself is exchangeable. So a mesh protocol can use, or might use, different physical layers for transmission. For example, Wi-Fi or the device-to-device transmission modes in upcoming 5G releases, or even existing ones. And it could use Bluetooth for transmission. It could use IEEE 802.15.4. And because, yeah, its tasks are taking place in different layers. So this leaves the last question to answer for today's lecture: how are wireless mesh networks cooperative? Remembering the example topology from before, again, this is not a mesh topology. This is a typical star topology from nowadays hierarchical networks. So having the base station in the middle, or the router in the middle, which is a dedicated hardware, dedicated node that performs the forwarding task, that is responsible for many things. Whereas in a mesh network, those tasks are spread to every node there. So any node can be a sender, can be a receiver, or a relay, so a forwarder. So this means that wireless mesh networks fulfill the reciprocity condition of being cooperative by nature. So the conditions 2, 3, and 4, detection and punishment of cheaters, invest into future cooperation, and tolerance in payoff, are a little bit harder to answer. First of all, many nowadays wireless mesh networks are on machines or inaccessible to users. For example, the backbone nodes in community networks, or let's say the nodes on windmills and wind parks. So the user cannot really modify this, and very often there's no interest in doing that. Take the wind park here. However, this is possible. So a user might or could lie about its forwarding rates, lie about its links. This is somehow protected by the fact that the mesh protocols are very often deep down in the kernel space. So modification would be possible, but is very unlikely. I can give a note here that there are blockchain-based approaches to overcome this limitation, but I'm not aware of any implementation of that. So the final point, the final condition for cooperative communication systems, the cognition of cooperation partners, is again a very easy condition for mesh networks, as any node approaching a mesh network can be recognized by hello messages or beacons that just include the protocol type. So as long as mesh networks speak the same language, the recognition of cooperation partners is super easy. So that's it for today's lecture. The next lecture is going to be about an example, and I'll explain in a more detailed fashion the inner workings of mesh protocols. So see you then.